Patrick.
All right, well, thank you very much for the invitation to speak here today. There's been an exciting set of collisions between quantum information science, which is the area that I come from, the study of the ways in which we can exploit the rules of quantum mechanics to do things that would be interesting or maybe even otherwise impossible from an information processing perspective, with other branches of physics. And this happened first, I think, in condensed matter physics, where ideas from quantum information gave rise to new algorithms for studying the properties of ground states. It's played an important role in understanding what is called topological order, so systems that have excitations that behave in a topological fashion. And only more recently, this collision has sort of happened again in what we could call high energy physics, or the study ultimately of, or the attempt to find a unified theory of quantum mechanics and gravity. So as I said, I'm an information theorist, but we've established this collaboration which brings together string theorists, quantum field theorists, relativists, quantum information people like me, to try to make progress on these questions. And so over the next hour, I'm going to try to bring you through a little bit of the history. I'll touch on a bit of work that I've done, but not too much, and give you an indication of why we think this is exciting. One of the members of the collaboration, a string theorist, is in the audience, Mark van Ramstok, and so I may need to defer to him if you ask me a string theory question. There are also other distinguished string theorists, and we heard from a distinguished relativist, a mathematician, this morning, and so there's almost enough expertise in this room to form a new collaboration on a similar topic. All right. So where does the title come from? It comes from a manifesto that John Wheeler wrote back in 1990, in which first I'll tell you who John Wheeler is, if you haven't heard of him. John Wheeler is a very distinguished physicist. He was Richard Feynman's supervisor. He coined the term black hole, wormhole. He coined the term moderator in the context of moderating the speed of neutrons in nuclear reactors. Really one of the giants of 20th century physics, also a very charismatic and inspiring person. And he felt that to really understand the mysteries of quantum mechanics and gravity, we had to more deeply understand the information theoretic nature of quantum mechanics. And so he said, "It from bit symbolizes the idea that every item of the physical world has at bottom, a very deep bottom in most instances, an immaterial source and explanation. That which we call reality arises in the last analysis from the posing of yes or no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin, and that this is a participatory universe." As I said, it's really quite a manifesto, that he really felt that the ultimate underpinnings of physics would be information theoretic. I don't know if we can go that far, but I'm going to try to convince you over the next hour that information theoretic thinking can be very fruitful. Wheeler placed a real emphasis on the fact that quantum mechanics involves measurement, and that's important, but as you'll see, the emphasis over the past 15, 20 years has shifted a little bit to a fully quantum mechanical theory of information in which measurement itself plays a slightly more secondary role. So this is about it from qubit. We have to talk about qubits. We have to talk about it. We'll start with the qubits. This I don't think many of you need to be refreshed on, but of course, if we have a laser, we shine that laser through a single slit, then what's going to happen if we project the result is we're going to get some monotonically decreasing intensity on a screen. But of course, if we have a couple of slits, then we'll see interference effects, and we'll get interference fringes on the screen from constructive and destructive interference. Now, one of the remarkable properties of quantum mechanics is that if we reduce the intensity of the laser to the point where it's emitting essentially single photons, one at a time, and we do the experiment, you might imagine, of course, or we might have imagined 100 years ago, that the photon would have to either go through the left slit or the right slit, in which case we'd see some uniform monotonic distribution of clicks at the other end. But if we do this experiment, what we find is a pattern of flashes from the individual photons, which corresponds in frequency to the intensity of the interference fringes of the laser. And so the photon has to be actually, in some sense, taking both paths and interfering with itself. So information essentials, if we're going to talk about bits and qubits, a bit is, of course, just a two-state system, somewhere where we can store a 0 and store a 1, like a switch. And a qubit is just going to be our basic information theoretic unit in quantum mechanics, a two-state quantum system. So if you're thinking about the photon, we could say that the photon going up was a 0, the photon going down was a 1. And as we saw, there are interesting states, even though a priori this is a two-state system, it's either going up or down, that involve both at the same time. And in fact, the state space in quantum mechanics is linear. The equation of motion is linear. And so if we have solutions, then linear combinations of those solutions remain solutions. And so 0 plus 1 is the solution corresponding to taking both paths. Or we can have some other coefficients there. Of course, this doesn't just apply to photons. It applies to essentially everything. And so if we had an atom, for example, we could say this is a hydrogenic atom with a single electron. We could identify the ground state with a 0, the first excited state with a 1, and we'd have our qubit. And a superposition of 0 and 1 corresponds to having both the ground state and the first excited state at the same time in some appropriate sense. It doesn't correspond to the electron being midway between those two energy levels. That doesn't exist as a solution of the equations. You could do this in other ways. Here's a double well quantum dot. So here the 0 would correspond to the electron being on the left side of this device, the 1 being on the right side. Something similar involving superconductors. There are as many ways to do this as you can, well, certainly as many as you could count. Now, if we actually want to talk about information, information is really about, well, requires that we start thinking about composite systems. And so if we had two atoms, we could then express not just the value of a single bit, but of a pair of bits, of course. And so ground could be our 0, 0, A for the left and B for the right. Our 0, 1 corresponds to one atom in the ground state, one in the first excited state, and so on for the other possibilities. And so here's a basis set for our qubit, set of distinct states. But as we've seen, we can take superpositions. We can take linear combinations of these possibilities, and those are also solutions. And so in particular, we could prepare a state that is a linear combination of 0, 1, and 1, 0. And so the way that, I apologize for the contrast there, when my electrons are yellow in this picture, I'm going to draw there we go. The second combination, I'll identify that, I'll label it with green. So my 0, 1 state is going to be yellow for the electrons, and the 1, 0 state will be green. And so a linear combination of 0, 1, and 1, 0 corresponds to having the atoms either in the yellow or in the yellow and the green at the same time. So the states are correlated between the left and the right. But it's important to say a definite state of the pair of atoms. This is very different than a probabilistic mixture of those two possibilities, in particular because I could construct an interference experiment analogous to the two-slit experiment with the atoms that would identify this state as being different than a probabilistic mixture of 0, 1, and 1, 0. All right, so those entangled states, as we've been discussing, represent some kind of correlation in quantum mechanics. But what's exciting about the correlation that exists in quantum mechanics, and the kind of thing that got Wheeler perplexed and thought needed some further explanation, was that these correlations could be very surprisingly strong. And so this is an old story. This is, of course, well known back when Wheeler made this observation, and for 20 years before that. When I originally made this slide, it was a game only a physicist could love, but then I realized we have physicists, computer scientists, and mathematicians, and I think all of us can love this game in our own individual ways. So here we have Alice and Bob, and there's going to be a referee. And the referee is going to give Alice a bit, and is going to give Bob a bit. And we should imagine Alice and Bob individually being deep in some basement somewhere. They can't talk to each other. They're separated. They have no idea what the weather is like outside. But the referee informs Alice that it's either rainy or sunny. The referee informs Bob that it's either hot or cold. And now Alice is going to have to output either a 0 or 1, a 1-bit output, and the same for Bob. And they're going to win at this game if their outputs satisfy a particular relation. So they want to, and the relation is, if the weather is good, meaning it's both hot and sunny, then the bitwise addition of their bits modulo 2 should be equal to 1. That is, the XOR of their bits should be equal to 1. So the way you should think about this is that they are performing some kind of distributed computation of the AND function of their two. Alice's bit is either a 0 or 1 at the input, likewise for Bob's. They're performing a distributed computation of the AND. So Of course, one way to do this might be to say, okay, well, Alice is going to output a 1 if it's sunny and a 0 if it's rainy. Bob is going to output a 0 if it's hot, a 1 if it's cold. And we can look at the table, and they're going to succeed in all cases, right? It's going to, the bitwise addition modulo 2 will indeed be 1 if it's hot and sunny, 0 if it's hot and rainy, which is bad weather, or cold and sunny. But we'll get the wrong answer if it is really bad weather, which is both cold and rainy, right? And it's kind of obvious that for any strategy that Alice and Bob adopt here, they're going to be wrong at least 1 out of 4 times, because, well, this is a necessary fact. And so the only way for them to succeed 100% of the time is for them to communicate, right? This is kind of clear. And the best strategy is either, well, for example, the one that I gave, but even simpler, they could just ignore their inputs completely and always output 0. And then they'll be right 3/4 of the time and only wrong when the weather is really good. Now, quantum mechanics allows us to do something interesting in this context, or actually before we get there, I should point out that as I've described it, Alice and Bob have to answer deterministically as a function of their inputs. But they could share correlation instead in this context, and then give their answers as a function of both some bit that is shared between them and the bit that is given to them. But in that case, their probability of winning is just an average over those shared random bits, and it doesn't help. But if we give them quantum mechanical correlation in the form of one of these entangled states, one atom goes to Alice, one atom goes to Bob, then Alice could perform a measurement on her atom that depends on her bit, and Bob could perform a measurement on his atom that depends on his bit, and then they could look at the outcomes. And it turns out that if they do this, they'll be able to win with a probability which exceeds 75%, which is 86, actually I think, well, around 86% of the time, cosine squared of pi by 8. And so this is the real demonstration. This is a Bell inequality. You've probably encountered this in some other form before involving some correlation functions, but I like to express it in a game, as it's very straightforward this way. And this might seem a little bit obscure, but this being able to win with a probability of 86%, if they could win 100% of the time, they still would not necessarily be able to communicate faster than light. You can find distribution or situations in which that holds. But for the computer scientists in the room, all of communication complexity would then become trivial, because they could perform distributed computations with essentially no communication. And so you'd have a world in which causality wasn't violated, but an arbitrarily complicated function of an Alice bit string and a Bob bit string could be a value with a single bit of communication. It would be a very strange world. And in fact, that statement remains true even if they don't win 100% of the time, but we know it remains true if they win about 91% of the time. And maybe with better fault-tolerant computational techniques, we could show that it remains true even down to 86% of the time. But we don't know that at this point. So that was a kind of a parlor game. But as I said, this is actually just a restatement of Bell's theorem, that if you have a theory of physics that assumes that signals can't propagate faster than the speed of light, and that objects have well-defined states prior to being measured, then you derive the constraints that we saw on the previous slide, the 75%. But we know that quantum mechanics and experiments violate that fact, and so one of locality and realism has to be wrong. And there was a kind of a landmark experiment that was just published earlier this week in Nature. The first loophole, these kinds of experiments have been done since the late 1970s, but the first loophole-free Bell experiment. And so if you were a real conspiracy theorist and you did not want to give up locality and realism, until last week, you could have held on to your beliefs. But that is no longer a tenable position. It has been ruled out. That experiment is most exciting because it managed to entangle the state of 2 defects in diamonds separated by 2 different diamonds about 1.3 kilometers apart, which I think is going to be important in the future for quantum communication. But as far as our understanding of the world goes, it really is just eliminated what was an increasingly untenable position already. So that's just a brief introduction to some of the interesting information theoretic properties of quantum mechanics. You've probably heard of Heisenberg's uncertainty principle. There are limits on what we can know that are fundamental to quantum mechanics. There's the whole story of quantum computation that came up in Oded's talk. There's a lot more to say, but I'm going to move on now just to to say a little bit more about the it. What was it that Wheeler wanted to have explained by these information theoretic ideas? And we actually had a beautiful introduction to black holes by Sergio this morning, and so you know all about them. Here is a picture, a rendering of what a black hole lensing would do to if we tried to look at some constellation with a black hole in the way. So as we learned this morning, or actually what we learned this morning is that these theorems are perhaps not as robust as I previously thought they were. But what are called no-hair theorems in general relativity tell us that black holes should be described by a small number of macroscopic variables. We heard this morning the mass, the angular momentum, also the charge is a possibility, but that's about it. And so if you have some matter, which is entropic, we also, Sharon told us about entropy this morning. So you drop some entropy, some system, some matter into a black hole and it has some entropy. That entropy corresponds to uncertainty about the microstate of the system. But if that system falls into a black hole, and the state of the black hole is subsequently described by these three macroscopic parameters, it seems like the entropy should have gone down. And this was a puzzle back in the 1970s. And Bekenstein, who unfortunately just passed away this year, proposed a resolution of this seeming violation of the second law of thermodynamics by saying that there should be entropy associated with the black hole itself, not directly with its microstates, but with its area, because the area was a property of the black hole that did increase when matter fell into it. And subsequent investigations, calculations by Hawking, of the horizon, yes, yeah. So the detailed formula is one of these great jamboree formulas in physics that involves just about a bit of everything, right? We have the Boltzmann constant, which is really telling us there's something statistical mechanical going on. The speed of light, it's about relativity. Newton's constant, the strength of gravity. H bar telling us there's something quantum mechanical at work. And of course, the area of this horizon, which is a geometrical quantity rather than what we would have originally expected, something sort of more microscopic. So the origin of this kind of mysterious form of entropy, it was a puzzle for many years. Like, what is it counting? If it's counting anything, because we're used to entropy counting microstates in some form. That was ultimately explained, at least for some reasonably large class of black holes, if not the ones that we encounter in nature, by Strominger and Vafa, by actually counting explicitly states in string theory, black hole microstates, and comparing them to this formula and seeing that they matched. But black holes, when we combine them with gravity, also present us with other problems and other confusion. And so if we have some matter that we prepare in a well-defined, understood state with no uncertainty in it, and we allow it to collapse to a black hole, Hawking did a calculation which indicated that the black hole should actually radiate. And that radiation will ultimately start carrying away the mass energy of the black hole, and the black hole is going to have to shrink. And ultimately, the black hole should disappear entirely, and so we'll be left with a bunch of matter again, no black hole. And Hawking's calculation, when he did it, indicated that the final state, the state of the radiation coming out of the black hole, was actually really a statistical mixture of different states. And this was this was not just a sort of artifact of some details of the calculation. It was a consequence of the fact that general relativity describes some causal structure, and nothing should be getting out of the interior of a black hole. And if no information is getting out of the interior of a black hole from the causal structure, that sort of logically entails the creation of some uncertainty in the evaporation process. And so Hawking posed the question, is the final state after the evaporation of a black hole mixed, meaning a statistical mixture of different states, or is it actually pure? And this is really a crucial question for the formulation of quantum gravity, because it's really just asking the question, is the microscopic physics of quantum gravity reversible or not? And in all the theories of physics we've encountered so far, the ones that really matter, the microscopic physics is reversible. And so if it were not, that would be a sign that something truly radical has to take place. And in particular, it would indicate that quantum mechanics, as we understand it, which is microscopically reversible, is fundamentally flawed. So leaving that behind for a little bit, This is the context that was motivating Wheeler to write his manifesto. And he inspired a number of young people who were in his orbit at the time to think about these questions. So there's a graduate student, a postdoc, and an undergraduate student at the University of Texas, where he was at the time. And these young people took his ideas to heart. But what they did was a little bit unexpected. This Bill Wooders, he found what is called the quantum no-cloning theorem, quantum teleportation, which you may have heard. These are both sort of foundation stones of quantum information theory. David Deutsch, who is the postdoc, he found the first problem for which a quantum algorithm provided an advantage over a classical computer. And Ben Schumacher, who was the undergraduate, he ultimately went on to coin the term qubit and figure out that there was a quantum theory of compression and data transmission analogous to Shannon's theory but with quantum mechanical constituents, and actually prove interesting theorems about it. So returning to the black hole, there was this problem about whether black holes destroy information, right? Whether the pure state becomes mixed or not. And back in 1997, some eminent physicists, including one member of our collaboration, John Preskill, they didn't know what the answer was, and so they decided to bet, although they had their ideas. So whereas Stephen Hawking and Kip Thorne firmly believe that information swallowed by a black hole is forever hidden from the outside universe and can never be revealed, even as the black hole evaporates and completely disappears, and whereas John Preskill firmly believes that a mechanism for information to be released by the evaporating black hole must and will be found in the correct theory of quantum gravity, they make a bet. And whoever wins the bet is going to be given an encyclopedia from which information can be extracted at will. So that was back in 1997. And about 10 years later, Hawking conceded the bet. So here is Preskill on the stage hoisting the baseball encyclopedia triumphantly. And we could ask what happened in the intervening time to make Hawking give up. I should note that Kip Thorne, who is perhaps a little bit more careful, has not yet conceded the bet. So there's a consensus building, but it is not universal. And what happened is that Juan Maldacena developed this idea of what is called the anti-de Sitter space conformal field theory correspondence. So it's quite a mouthful. But the idea is that he gave us a way to formulate a theory of quantum gravity. It's not a theory of quantum gravity for our universe. It's for a slightly different kind of universe. But nonetheless, it seems to be a self-consistent way of thinking about quantum gravity, which is a major advance. So what are the properties of this setup? The basic idea is that you want to study quantum gravity in a box. If you've ever studied physics, it's much easier to put your system in a box and then take the limit where the box becomes large. And so if you want to do the same thing with quantum gravity, studying quantum gravity in anti-de Sitter space gives you that box. So it's a space-time. I've depicted it here as a cylinder. Time is going in the vertical direction. And there's a boundary to the space-time, which is the surface of the cylinder. And that's a time-like boundary, right? And then there's some bulk of the space-time, which I've depicted up here. And events are supposed to happen in the inside. And this quantum theory of gravity is going to work in the context in which the space-time is asymptotically this anti-de Sitter space. And I'll tell you a little bit more about what it is soon. But the interesting thing about it is that quantum gravity is this very complicated thing. String theory, maybe other phenomena we don't know about at this point. But the correspondence tells us that the quantum theory of gravity in this bulk is going to be equivalent to a vanilla, old-style quantum theory of some substance living on the boundary without any gravity in it. So you can get rid of gravity entirely and just talk about a quantum field theory. And it's quantum field theory with some special symmetry. It has a scaling symmetry, so it's a conformal field theory. But what it tells us is that a quantum field theory on the boundary is equivalent to a quantum gravity theory in the bulk. So the gravity theory, if you'll notice, has one extra spatial dimension. So one of the spatial dimensions here is actually emergent. And that is one of the beautiful properties. And this proposal that was made back in 1997 based on string theory calculations has since been the subject of a huge amount of investigation, 15,000 citations, and it has held up remarkably well. It hasn't been proven, but there is substantial evidence in favor of it, and analogous similar results. So if we take anti-de Sitter space and take a spatial slice of anti-de Sitter space, it's actually just a hyperbolic space, right? So it's a negatively curved space of constant curvature. And the geodesic, so you can think of it, here's an Escher rendition. The metric to count distances between points is the fish counting metric, the minimum number of fish you need to pass through to go from point A to point B. And the theory is not just a theory of empty anti-de Sitter space. We can put matter in there and find out what happens. In particular, we can put a black hole, and that will distort the geodesics. So rather than following the fish, that will, well, the metric will be changed. We know how it will be changed. So this ADS-CFT correspondence was essentially the reason that Hawking conceded the bet. And the reasoning went as follows. If quantum gravity is equivalent to a standard quantum mechanical theory without gravity, and we know that standard quantum mechanical theories are unitary, they're microscopically reversible, then even if we don't understand the details of black hole evaporation, because we can map the problem onto a standard quantum mechanical theory which is reversible, information must not be destroyed. And so that's why Hawking conceded the bet. But we're going to move on to some other questions now, for which, yeah.
Can you say, just finish that? So when you map it onto the boundary, field there on the boundary,
Yeah.
how does the evaporation work?
So black hole states generally correspond to thermal states in the boundary theory. But this space-time has it has this time-like boundary. And what happens is that if you have a big black hole in there, then the radiation coming out off of the black hole will hit the boundary and come back in finite time, and the black hole will equilibrate with the boundary and not evaporate. It will just. But if you have a small black hole, then it can then it will be able to evaporate before the radiation can go out, hit the boundary, and come back and reach equilibrium. And so you could, in principle, you could think of a setup where you send in some matter that is going to collapse to a small black hole, but then the small black hole is going to evaporate away. And that process in the boundary theory should be unitary, and therefore microscopically reversible. OK. So here, I want to talk about a black. So this morning we had a discussion of whether black holes were real. There are beautiful mathematical constructs, and we can ask whether they are physical. So this is going to be an example of a black hole which is most definitely not physical, not just because it's an anti-de Sitter space, but because it doesn't form from collapse. But nonetheless, it has some interesting lessons for us, I think. So this is one of these Penrose diagrams that again came up this morning, but I'll go through the setup again. So for each point, there is a light cone which defines the future of that point. So all light rays emanating from that point are going to be within the light cone. And so in this region here, I could send some light rays out towards this boundary. This is the time-like boundary of the theory. I can also send light rays in this direction. If I have a point in this region, and I've identified the singularity as this space-like surface up top, then we see that everything in the future of that point has to hit the singularity. And so all points in this upper V correspond to points in the interior of the black hole, whereas points on the right-hand side are in the exterior of the black hole. Now in this particular geometry, though, we see that there's another region which is symmetric, right? Left-right symmetric with the exterior region over here. And so from this left-hand side, I could also fall into the black hole and reach the interior. And so this black hole is a bit of a funny thing. It's a black hole with two asymptotic regions that are joined at the interior of the black hole. And this sounds exotic, but this is the natural object that you get if you just construct a black hole, in this case an anti-de Sitter space, and then perform the maximal analytic extension. And the same thing happens in the Schwarzschild case. It's not special to ADS. So we have two asymptotic regions, each of which contain a black hole, and they're joined in the middle. And so this thing here actually describes a wormhole, but it's a non-traversable wormhole. You can't go from one side to the other, because your only way to get inside the wormhole is to jump inside the black hole. So two people in the two asymptotic regions could meet in the middle and confirm the existence of the other side, but they could never tell anyone about it. All right, so in the anti-de Sitter space conformal field theory correspondence, the state associated to this two-sided black hole is a very interesting thing. So remember that quantum states can be written as linear combinations of, well, if I have some solutions, then I can take linear combinations of the solutions to get new solutions. And so the state describing the two-sided black hole at this time right here is a linear combination with what these Boltzmann-type weights of a state on the left and a state on the right. And the states on the left are states of the conformal field theory associated with this left-hand time-like boundary. States on the right are states of the conformal field theory associated with the right-hand time-like boundary. And so a typical state here on the right corresponds to a one-sided black hole. And a typical state on the left corresponds to a one-sided black hole on the left. And whatever the states are on the left and the right, they correspond to some asymptotically anti-de Sitter space with a single boundary. But what we find is that when we take this big linear combination with the appropriate weights, these two disconnected geometries get fused together into a single geometry linked by a wormhole. Right? That's actually formally what is happening here. And so entanglement between the left-hand conformal field theory and the right-hand conformal field theory manifests itself as space being created between the two. And this was first observed by Maldacena in 2003. Yeah?
So I understand entangled between particles or something. What's entangled between two?
Oh, sorry. So I should say that the theory has a state space associated with it. Right? So the conformal field theory, you should just think of it as the quantum theory of some exotic material, right? And that exotic material has a state.
What do you mean by theory of?
So theory, let me say there's a Hamiltonian, and I'm going to be interested, say, in the ground states or the thermal states associated with that particular Hamiltonian. And that Hamiltonian also acts on a particular Hilbert space, so there's a Hilbert space which describes the space of states. Sorry, that language is a bit imprecise. When I say entanglement between the theories, what I really mean, there's a Hilbert space associated with the left, a Hilbert space associated with the right. And the Hamiltonian in this situation, quite remarkably, does not involve any interactions between the left and the right sides. So there's a Hilbert space for the left and a Hilbert space for the right. And the Hamiltonian is a sum of terms, one for the left and one for the right. They're pretty much the same Hamiltonian, up to some CPT conjugation.
And so wormhole is something that information gets. What do you mean existence of a wormhole?
So a wormhole here is really like if I take this space-like slice right here and ask what is the geometry, right? So the geometry, it's some three-dimensional geometry, and it looks like a tube, and that tube goes from the left-hand side to the right-hand side. So that's what is meant as a wormhole, right? It's a way it's something that connects the left-hand side and the right-hand side. But the causal structure is such that if you actually, the tube is changing in time, and so if you actually tried to move through the tube is changing in time, and at some point it hits the singularity. And so you'll never be able to make it out the other side because you'll hit the singularity before you actually get to the other side because you're constrained to not move faster than the speed of light. So it's a connection between this exterior region and that exterior region. And non-traversable means that there's no way for an observer to actually move from here to there. But the spatial connection nonetheless exists. Yes, so it is a possibility that you could have someone fall in from the left, someone fall in from the right, So sort of following a trajectory this way, another trajectory that way, and they'll meet in the middle. And so they'll be able to announce triumphantly to each other that a world that you did not know about exists, and they would cheer and then get destroyed. Yeah. Does that answer the question? Okay. Yeah.
So what is such a state ever formed?
Sorry?
How do you form such a state?
How do you form such a thing? As far as I know, you can't. I mean, there are string theorists in the audience. Do any string theorists have a proposal for how you could? Oh, actually, yeah. It's like from a mathematical perspective. I think if he was asking how you would make such a state. Yeah.
Okay, so such a thing could be made in the white hole region, not in the experience. So we can't, but could be made by.
Oh, so yeah. So I mean, if you can create the initial conditions somehow, then you'll eventually end up with the wormhole. I think there may be some results about the creation of entangled black holes and magnetic fields. Is this something that happens?
I mean, another perspective would be the CFTs. If you wanted to think of the CFTs as something you had control over, say, some system in a lab that was described by the Hamiltonian, you could certainly try to produce that state directly, and then you'd be describing the space-time, so it would exist.
And so at some point, there should have been interactions between the two CFTs.
To establish the entangled state in the first place.
Yeah.
Yeah.
White hole your bottom triangle?
Yes, it's a time-reversed black hole. Right. So nothing. Instead of nothing being able to get out, nothing is able to get in to this region here. Yeah.
Can I ask another question?
Sure.
So now I'm actually confused. So what was that Hamiltonian for? It's for the black hole,
It was for the whole system.
which is what?
So it's two copies. There's a Hilbert space for CFT1 or CFT left, a Hilbert space for CFT left or right, and then there's a Hamiltonian, which is the sum of a CFT left and CFT right Hamiltonian. And then this is a state in that theory.
But what are left and right? These are in pieces of material in two places?
Oh, okay, yeah. So if we want to,
Sorry,
yeah.
I didn't hear that.
But like from the perspective that Mark was giving, if you wanted to set aside this gravitational story, the CFT could correspond to the physical theory describing some material, right?
Yeah.
And so there'd be some material here, some material there, and they'd each have their own Hamiltonians. They wouldn't interact, and then this would be a state of the two materials entangled together, and then would have an interpretation, a gravitational interpretation like this, if it was the right kind of theory. Okay, now the question that we really want to answer is whether space-time actually does emerge from entanglement, because in the previous slide there was an indication that it did. And to get there, we had to be a little bit more quantitative about how we measure entropy in quantum mechanics. And so here was the state of two atoms that we were talking about, 0, 1 plus 1, 0. And if I measure the first atom, what I get is a 0 with probability 50%, a 1 with probability 50%. If I measure both of them, I get 0, 1 with probability 50%, or 1, 0 with probability 50%. But measurement in quantum mechanics is actually something that is a little bit flexible. I'm not forced to always measure the same thing, and any orthogonal basis of the state space corresponds to a valid measurement. And so I could measure, instead of 0, 0, 0, 1, 1, 0, 1, 1, this more complicated thing, a different orthogonal basis, 0, 0 plus 1, 1, 0, 0 minus 1, 1, and so on. And if I measure in this second basis, of course, what's going to happen, 100% of the time I'll report, or the experiment will report the state was 0, 1 plus 1, 0. And so if I now want to associate entropies to these different subsystems, or these different measurements, in the first case, I clearly have one bit of entropy. In the second case, I have one bit of entropy. In the third case, for the same system, but with a different measurement, I have no entropy at all. And so the quantity, which is the entropy in quantum mechanics, the von Neumann entropy, what you have to do is you minimize over all different possible ways of measuring the system how much entropy you would get. And so the entropy of the first atom alone is going to be 1. There's no way to reduce that entropy. But we've seen that for the pair, we can reduce the entropy to 0. And so the joint entropy is 0. And this is kind of quite a remarkable thing, if there are any probabilists in the audience. Because if I have two random variables that are jointly distributed, like say one of them describes whether it's going to be hot or cold, and the other one describes whether it's going to be rainy or sunny, I am more uncertain about the pair of random variables than I am about the individual one. But here we see you can be more uncertain about the part than you are of the whole, right? And this is a signature of the presence of entanglement. In the context of ADS-CFT, we can do the same kind of thing. Instead of only looking at one atom out of two, we can look at one part of that material and ask what is the entropy associated with some, say, spatial region of material if we look at just, say, part of the ring up here. And back in 2006, I believe, Ryu and Takiyanagi made a proposal for how you should calculate that entropy. And if you think about the calculation, in the absence of this holographic correspondence, it's a nightmare, right? You're going to have to minimize over all possible measurements. You have to know something about the structure of the state. Like it has been done for some interesting materials, but it's a hard thing. The proposal is that to calculate this entropy, you just have to calculate the area of a minimal surface, right? Something very simple. And the minimal surface, you just minimize over bulk surfaces that are homologous to the boundary surface that you're interested in. And this has been verified in a number of examples. And at this point, we even have a decent argument that it should be true in general case, at least for static spacetimes. And this proposal is really very interesting and exciting because it generalizes the Bekenstein-Hawking black hole entropy formula. Whereas Bekenstein-Hawking associated an entropy to a very particular region in space, right, to a black hole, and it was the area of the horizon. Now we're able to associate entropies to minimal surfaces in these holographic geometries. And the Hawking calculation that then just becomes a special case, we ask, what is the entropy of the whole A system, the whole boundary, in one of these two-sided black holes? And it turns out that the minimal surface gets hung up on the horizon. And so it just measures the area of the horizon. So, oh, yeah, so I was going to say a little bit more, but I decided to skip it. The point is just that if you have a pure quantum state that is not a statistical mixture, then this von Neumann entropy is actually precisely measuring the entanglement between the part you're interested in and its complement. And so that the length of this minimal surface then becomes a surrogate for the entanglement between A and its complement. Yeah. Oh. Oh yeah. So in this case, I should have drawn a second CFT, right? So think of the two-sided black hole, and so the complement is the second one. Yeah. Yeah. Yeah.
So what do you mean by saying that this is a proposal? So is it conjecture to equal von Neumann entropy? Is that what you?
So it was originally conjectured, and the evidence was a number of examples where you could compute and see that these were equal. And it has since been demonstrated, assuming some other aspects of the ADS-CFT correspondence. And there are some further caveats that I think include, there's some saddle point approximation calculation that goes on, and so assuming that there are no complex saddles that you have to worry about. So there are caveats to this argument. And it's also only actually the leading order term in the entropy. So there are corrections. Leading order here with respect to some parameter which counts the number, the density of degrees of freedom in the conformal field theory. So as you get to, yeah. So, OK. So I think there are a number of computer scientists in the room. And so those computer scientists will be, well, and probably most of you will be very familiar with entropy. It's information theoretic interpretation. It governs the optimal rate at which you can compress some source. And so in this context, we could imagine, say, some Alice having access to the A portion of a material and wanting to send it to a Bob. And this is now a quantum material, so she has to do quantum compression. But thanks to Ben Schumacher, Wheeler's undergraduate student that I mentioned earlier, we know how to discuss this, and the cost is going to be given by the entropy of that region, the von Neumann entropy. And so the length of the curve governs the length of this curve governs the minimal cost of compression. But that means that there's there are two interesting optimizations going on. The minimal compression cost is equal to the length of the minimal length curve. And then that suggests the possibility that something interesting would be going on here, some interpretation of more general curves in the bulk in terms of some other type of compression protocols that are not necessarily optimal. Oh, yeah, so let's just restrict ourselves now to the case where the bulk is 2 plus 1 dimensional, and then they're really curves. These statements generalize up to a point to higher dimensions, but yeah. Right. No, the number of time-like directions remains 1. It doesn't become strange in that regard. Yeah. Yeah, so now I'm just looking at a spatial slice. Yep. So the analogy that I'd like to give is streaming compression a la Netflix, right? So if you want to watch a movie online, the minimal number of bits that Netflix would have to send you would be to, they would achieve that by compressing the whole movie at once and then sending you the whole thing. Of course, they don't do that because you'd have to wait 20 minutes before you could start watching. And so instead, they do some kind of streaming compression that exploits, say, high-frequency correlations in the movie and also long-range correlations. So in this case, I was looking at some consecutive frames, but we also have an actor. The actor's face doesn't change throughout the movie, so you only have to animate the face in principle. You don't have to actually send it every time. Now, in practice, they don't make very much use of these infrared, long-range correlations. They make use of the UV correlations. And as a consequence, the compression cost is increased. In this holographic setting, given a bulk curve, we can actually map it onto a class of streaming compression protocols. So here I have a bulk curve up top. So my boundary, I've now drawn it as straight. So my boundaries have been round or have been circular. So let's just open them up, make it straight. And then I have a curve up top. So at each point on that curve, I could draw a tangent vector and then extend that tangent vector to a geodesic. And that geodesic will intersect the boundary in 2 points, right? And so I can associate to each curve a sequence of boundary intervals. And so those boundary intervals are going to define a streaming compression protocol. Then my Alice is going to have access to those intervals each in turn in her laboratory, and Bob is going to have access to the same intervals in his laboratory. So we've now imposed locality and scale constraints on the ways that Alice and Bob are allowed to compress, and the cost is therefore going to have to increase. And one can prove, I've called this a theorem, but perhaps given Sergio's earlier talk, I should not call it a theorem because it assumes the ADS-CFT correspondence. There is a theorem underlying this, but the length of a convex curve is, in fact, the minimal qubit cost required for Alice to transfer the subtended portion of her boundary state to Bob in a streaming compression protocol with curve-dependent locality and scale constraints as I've described. And so we really can interpret the length of general curves in this information theoretic way. So I'm going to skip this here. This is now a space-like slice, so it's just the regular metric, or the space-like portion. I'm afraid I'm going to skip this here, but I'd like to take you through one final piece of the story, because the question that we wanted to ask was: is space-time stitched together by entanglement? Is entanglement let's leave it at that. All right, so. Another formula for the von Neumann entropy that I introduced earlier, there's an operator called the density operator you can associate to a quantum state. Let's call it rho. It's just going to be minus the trace of rho log rho. An even more important quantity than the von Neumann entropy is something called the relative entropy. It has a formula in terms of the density operator there. Those of you who know information theory will recognize this. It looks a lot like the Kullback-Leibler divergence. Right, so it's a quantum mechanical version of that. This function is equal to 0 if the states are the same. Otherwise, it's strictly positive. And so we could think about the relative entropy. I should say this is work by Mark van Romstonk and his collaborators, who's in the audience, for a state and a state very nearby, rho plus delta rho. In that case, this inequality at first order has to become an equality, right? Because we have to have a local minimum. And so we get an equation that the changes in entropy are equal to something, and that something turns out to look like a change in energy. And this becomes a generalization of the first law of thermodynamics. And if you just take this, this observation and then apply it using the Ryu-Takiyanagi formula to all boundary spheres of different sizes, and in fact, boundary spheres in different reference frames, where you allow yourself to boost to frames that move relative to each other at different speeds, then what you find is that this first law of entanglement entropy, this generalization of the first law of thermodynamics, becomes Einstein's equation to linear order in the bulk. And so the moral of the story is that quantum mechanical consistency of the boundary theory implies Einstein's theory of general relativity. So 25 years ago, or even more recently than that, the program was that we should try to quantize gravity. Right? We have gravity as a classical field theory, write down, try to do some canonical quantization or something, and then end up with a quantum mechanical theory. Here we're getting a very different perspective, that in fact gravity, the theory of gravity, can emerge from quantum mechanics itself, just from consistency with quantum mechanics. Of course, this is in the context of the ADS-CFT correspondence, which is quite limited. We don't know that it holds in general, but I think it's an exciting clue. And I should probably leave there. The general message is that entanglement, which is this crucial feature which separates classical and quantum mechanics, ultimately really seems to be crucial to the structure of space and time itself. And a detailed study of entanglement and its consistency and its information theoretic properties seems to go a long way towards allowing us to derive the theory of gravity. And I should end there, I suppose.